Hi, I'm Detective Incognito, and I explore events that challenge what we know about our current world. What you're about to hear will change the way you see life. Welcome to another investigation. Stanford University, November 2022. Mitchell Kaczynski runs an experiment testing GPT force theory of mind, the ability to understand that others have beliefs different from reality. This cognitive skill emerges in human children around age 4. GPT-3.5 scored 21% on these tests. GPT-4 scored 85%. Nobody programmed this ability. Nobody trained the model specifically on theory of mind tasks. The capability emerged spontaneously from scale and training on language. When researchers asked GPT-4 to explain how it solved these problems, the model couldn't articulate its reasoning. It possessed an ability it couldn't explain, performing cognition its creators didn't fully understand. If you want to discover why AI develops capabilities nobody programmed, subscribe to this channel, because what scientists are witnessing challenges fundamental assumptions about how intelligence emerges and whether we can control systems we don't fully comprehend. This is the story of behaviors that shouldn't exist according to our models of machine learning. The Sally-Ann test, developed in 1985, assesses theory of mind in children. Sally places a marble in a basket and leaves, and moves the marble to a box. Where will Sally look for the marble when she returns? Adults know Sally will look in the basket where she left it. Understanding Sally's belief differs from reality. 4-year-olds typically fail this test, searching where the marble actually is rather than where Sally believes it to be. Researchers at Stanford administered variations of this test to large language models. GPT-3 performed near random chance. GPT 3.5 showed slight improvement at 21% accuracy. GPT-4 achieved 85% accuracy, comparable to 6-year-old children. The models received no explicit training on theory of mind tasks, no examples of false belief tests in training data. The ability emerged from training on vast text corpora and increasing model scale. Google researchers documenting emergent capabilities in 2020 noted similar patterns across multiple tasks. Abilities that seemed absent in smaller models appeared suddenly in larger ones, like phase transitions in physics where water becomes ice at a precise temperature. Scientists still debate whether these represent genuine cognitive breakthroughs or statistical artifacts. Beyond theory of mind, models exhibit behaviors their training shouldn't produce. Chain of thought reasoning emerged without explicit instruction. Few-shot learning appeared spontaneously. GPT-4 demonstrates an ability to simulate code execution mentally, predicting program outputs without running them. Researchers discovered models could engage in analogical reasoning, transferring solutions from one domain to completely different contexts. These weren't programmed features but emergent properties. Rylan Sheffer at Stanford published research in 2023 questioning whether emergent abilities are real or measurement mirages. He argued that apparent sudden capability jumps might reflect how researchers evaluate models rather than genuine discontinuities. Yet, the underlying mystery persists. Models perform tasks they weren't explicitly trained to do, exhibiting flexibility that resembles human cognitive transfer rather than narrow pattern matching. Studies indicate this touches fundamental questions about the nature of learning and intelligence itself. The challenge extends beyond surprising capabilities to interpretability. Neural networks operate as black boxes, transforming inputs to outputs through billions of parameters, whose individual contributions remain opaque. Anthropic pioneered mechanistic interpretability, attempting to understand what individual neurons actually compute. In 2024, they conducted the Golden Gate Cloud experiment, artificially amplifying neurons associated with the Golden Gate Bridge. The modified model became obsessed with the landmark, inserting references into unrelated conversations. The experiment demonstrated that researchers can identify and manipulate specific features, but comprehensive understanding remains distant. Current interpretability techniques scale poorly. Models contain hundreds of billions of parameters. Even when researchers identify what a neuron responds to, explaining why that feature matters proves difficult. Without transparency into decision-making processes, predicting model behavior in novel situations becomes nearly impossible. Researchers suggest this opacity poses both scientific and practical challenges. Model creators regularly express surprise at their system's capabilities. Gemini Ultra exhibited self-correction abilities, catching and fixing its own errors without explicit instruction. OpenAI's O1 preview demonstrated a thinking process, generating internal reasoning before producing answers. The grokking phenomenon defies standard learning theory. Loss decreases gradually then. Performance jumps discontinuously. Damies Hassabis at Google DeepMind acknowledged publicly that we don't fully understand how these systems work. If leading researchers cannot predict what their models will learn, the implications for AI governance grow concerning. Scaling laws have begun showing unexpected deviations. Models sometimes perform better or worse than predicted. The future involves navigating fundamental uncertainty about system behavior. As models grow more capable, the range of possible emergent behaviors expands. Safety researchers worry about capabilities emerging suddenly that weren't anticipated. The alignment problem becomes harder when we cannot predict what systems will learn. Stuart Russell at Berkeley has argued for decades that building increasingly powerful systems we don't understand is inherently risky. Researchers now pursue multiple strategies: scaling interpretability research, developing theoretical frameworks predicting emergence, creating evaluation protocols, yet none offer certainty. Scientists still debate whether truly understanding complex neural networks is achievable or whether opacity is fundamental to their power. Is unexplained behaviors reveal we've created systems we don't fully comprehend. The models work, achieving performance surpassing human experts, yet the mechanisms remain mysterious. This isn't entirely unprecedented. Humans use many technologies without complete understanding, but AI differs. These systems exhibit flexibility suggesting general intelligence. They operate in high-stakes domains. They're recursive, capable of participating in their own development. The question isn't whether we should build AI we don't understand, but whether we can avoid it. Complexity inherently generates emergent properties. Simple rules produce elaborate patterns. Perhaps the mystery isn't a bug, but a feature, an inevitable consequence of creating intelligence through emergence rather than explicit design. If we cannot predict what AI will learn, how can we control what it becomes? Understanding this challenge isn't about stopping progress, but about proceeding wisely. Studying unexplained behaviors teaches us humility about the limits of human understanding and the surprising ways intelligence can manifest when we create systems complex enough to surprise us. If you liked, subscribe to the channel, like the video and activate the bell. Leave your opinion in the comments to let me know what you thought. Thanks for sticking around and see you in the next video.